So, welcome. We are still concerned with the whole topic of multidimensional differential calculus. Very important terms here have already been used the previous time. We introduced something about potential functions, which are scalar fields. Now, finally, we have arrived in the three-dimensional space also, so we won't look at two-dimensional examples anymore, at least for a while. And we found out the connection between a potential and a gradient field. So because the gradient field is simply the vector field that you get when you take the gradient of a given potential. So that's quite a simple connection, actually. We could also say this scalar function called potential is sort of the primitive of the corresponding gradient field. You could also say the gradient field is the derivative, let's say the three-dimensional derivative of this potential. So this is, as always in calculus, this is a one-to-one relation of the sort derivative, antiderivative, but in a special sense. And this is why we also introduced spatial differential operators. Better speaking, we just introduced the gradient, which is the first and probably most important kind of first order spatial, well, yes, differentiation operator. The other two, which we know and which we will look at now, are called divergence and rotation. Sometimes also this is called curl. You may know what it means. Curl has this. It's you could say it's a feature, sort of a feature or a property of such fields, especially fields which are so-called vortex fields. So they have a certain vorticity. I can't give you a different word for that. It's just called, but you know what I mean. So a vortex is like when your field vectors are arranged around a circle, sort of that. They point, and if you go along a circle, they point more or less in tangential direction along this. It needn't even be a circle, just some sort of closed curve, right? And if you find a situation like this, you may suddenly understand that this sort of field can never be a pure gradient field. There's a strong connection between the fact that a potential scalar function, which has a gradient field, never generates a field where these field vectors are arranged in this way so that they, well, point in the direction of a certain curve which is closed. And the reason is quite simple. It leads us to the also to the coining to say that a gradient field is a conservative field. Now it helps to think physically in this situation, to think about mechanics where you know that, for example, gravitation, or also a very good example, as always, is electrostatic force. These kind of forces never generate energy out of nothing. And that's why you cannot find a situation, if this is a force field situation like this. So let's stay mathematically as mathematical as much as possible. So we just look at a certain potential. We want to know its gradient field. We want to calculate it. And then we find out this is a conservative vector field, as explained. So in the end, this is, it is sufficient to know that it is the gradient of a potential is sufficient in order to say it's a conservative vector field. So now we want to know what is the divergence of this vector field. I forgot to say that divergence and rotation are the two first order differential operations that can always be applied to vector fields, not to potentials, so not to scalar fields, while gradient is always applied to a scalar field only. So this is something where you see you can really easily hold them apart, but also you can combine these operations, and then it gets interesting. Okay, so we want to know the divergence also, and the curl, or let's say rotation, because this is also the short rot is the short symbol for doing so, of this vector field. And one of these, either divergence or rotation, turns out to be 0. So it vanishes everywhere in space. And we want to understand why. Okay, so the potential is given. It's quite simple, as you see. It's easily to be seen that this is nothing else than the squared distance from the origin. Take any point in space, calculate the squared sum of its components, or of its coordinates, and you will see, okay, this is nothing else than the squared distance from the origin. In spherical coordinates, this would simply be r squared, okay? Little r squared. So it's sort of unnatural, because it would mean, if you think of energy, this would be sort of a potential energy which rises, or which increases if you go away, if you could say, if you move away from the source of energy. So this is quite unrealistic, but the characteristic that it's spherically symmetric is very typical. Think of well, electrostatical force or gravity, and you find this term also in the let's say in the classical equation of gravitation and Coulomb force, but you will not find it simply there and nothing else. You will find it sort of 1 over this, or 1 over this square root and things like that. Okay, it doesn't matter so much what it means technically now, but since it's a valid potential, we can take the gradient easily, and we do so by, remember how to do it, and also try and get familiar with this nabla notation, which is a very famous short form of saying we want to take the derivative of the scalar field phi. So this is sort of a pseudo vector which contains simply the instructions to take the partial derivative for x, for y, for z. This is what's inside the nabla. And the phi is, you could say, is multiplied to nabla, which means that every time phi is differentiated. But then with respect to the corresponding variable. So it means for the first component of this vector field, you have to take the partial derivative for x, then for y for the second, and then for z for the third component, always referring to the original scalar function. So this is easily done. We all know that. Now remember how to take the partial derivative here. Of course, x squared, differentiated for x gives you 2 times x. Also, these two are additional constants, additive constants. It's constants in the sense that they don't depend on x. Okay, you remember we leave them alone, but it means in this case they go away when taking the derivative. And the same holds analogously for the second and third component. Here, I take the derivative for y. So this is additively constant, this is additively constant, this gets to be 2 times y, and same thing for the third component. So what do we find? We find, taking this common factor of 2 outside, it's nothing else than 2 times the radius vector itself. So this is something very special, okay? This is a gradient field which points outward with an increasing strength. Again, this is unrealistic, technically speaking, but mathematically it's absolutely okay. So it's also radially, you could say, spherically symmetric. It's a radial field. You could even say it's a divergent field. So this is what divergence means. In a sense. And okay, that's it. 2 times the vector which points from the origin to this point in space. But remember, this is a vector field. So this vector is the corresponding, let's say, force vector to be constructed in this point in space, away from the origin. So it's parallel to the radius vector itself. Let's just make a little sketch. If this were the origin and you point here, so this is your point in space. Let's call it P. Then the corresponding vector field F vector, yeah, the vector of in this point would be twice this one, like pointing still away from the origin, but with double length. This would be the vector F at this point in space, just for your imagination now. Okay, so let's look and see, because we now take the divergence of this vector field. And what is it? Well, you should have learned. I'm sure you have. Also, I give you these nabla notations, which is quite interesting. You can use the same symbolic operator nabla vector, which, as I told you, did I give it here? I think I didn't. It's sort of like this vector which says, please take the partial derivative for x, for y, for z, of whatever it gets. And these are placeholders, you know, these little dots are placeholders for whatever comes. Just right before, it was phi to be put there everywhere. This time, this is a scalar product, which means we have to, well, take the scalar product of this nabla pseudo vector with the given vector field. So you would say, okay, I multiply with f component 1, 2, 3, and you see what you get. Then it will be the first, of course, you have to combine this some way. It will be the first vector component to be partially differentiated for x, the second for y, the third for z, and the sum of all these, okay? So this plus this plus this is how you build a scalar product. This is just a formal trick to remember how nabla, well, has to be used when applied to a vector field. Also, we will see that the so-called rotation corresponds to a vectorial product between nabla and field. So let's stay here. We get, or we need, first field component partial derivative for x, plus the second partial for y, plus the third partial for z, as I always shortly say. Yeah? When I say partial for z, I mean partial derivative with respect to z. So, but this is simple, of course, since here this is our field. You see that this one, this component differentiated for x gets you 2, constantly 2, then plus the second for y gets you 2 again, and the third for z gets 2 again. So it actually, yes, it is 2 plus 2 plus 2 equals 6, constantly 6, which is not equal to 0, and means that this vector field has divergence. And as I told you, since it points outward everywhere, this is the perfect case where you can say there is divergence, because now you must think in the picture of let's say a fluid field, a field where the vector represents the strength and direction of, say, a fluid streaming somewhere, or even a gas. So this is a very vivid way of imagining what we mean when we say we have a divergent field. So there's no dynamics here, since an electrostatic field, for example, it doesn't change. But in this picture, in this imagination, it's like if it were a field where some fluid or gas streams from A to B. So this is just sort of an analogy. You don't have to take it word by word. So, okay, in the end, now this means that the divergence is not 0. And in the exercise, it says that one of them should be 0. So probably it will be the rotation, and we will find out why. So what is rotation? How is it taken? Well, as I told you, take the vector product. This is just for you to remember how to do it. I have my own way of remembering it, which is always just a simple circle diagram. Perhaps you like it. I just, in my mind, I say 1, 2, 3, and then I go round and round. You know what I mean? I go always in a circle. So my counting is now like in field algebra. I count 1, 2, 3, 1, 2, 3, 1, 2, 3. Always the same. Okay, always internal. So why do I do this? Just to remember that I now want to calculate the first component of the rotation of f in this case. And this means, by the rules of vector product, I have to take, look, it's characteristic that you never take anything which has to do with the first component. See here, 3, this is the second variable, and 2 and the third variable, but never you get 1 inside this row, and never you get x, the variable x. So it's sort of mixing it up, but in a regular way. You know what I mean? I'm in the first row, and then I say in my mind, I say second times third. Second times third means, in this case, second of nabla times third of f. So more clearly speaking, it means take the third component of the vector field and then take the partial derivative for y, because y is the second. So you know the second of nabla is on the left side here, f is on the right hand side, but the notation is as usual. So it means I have to say 3 comma y. This is just for reasons of convention, that it's this way and not the other way around. Okay, but anyway, remember it. Just remember it as well as you can, and find your own rule of or help system to remember it correctly. Now, the next step is just take minus vice versa. You remember? I think. Oh, now I remember. I have already used. We have already exercised how to take the vector product many weeks before. Okay, so second row, take go around. Okay, second. Now I need third times first. In other words, third of nabla times first of f. So f1 is differentiated partially for z. Z corresponds to the third component of nabla. So that's my way of remembering it. Then always minus vice versa. So if I get f1 comma z, next is, so this is, you could say 1, 3, and then I get 3, 1 here. So f3 differentiated for x. Third row, going around, 3. Next is 1, 2. So first times second, first of nabla times second of f. So I take f2 partial derivative with respect to x minus the other way around, first component partial derivative for y. So that's all. And now let's carefully do so. These are the components of our vector field. So the third component differentiated for y gets us 0 because it does not depend on y. There's no y inside. Now, minus the second for z, the second does not contain z, so again the derivative is 0. I get a 0 minus 0, which is 0. So you will note that this is clearly what happens all the time, because there is simply no dependency. Also, there's no dependence of the second component here from or on z or on x. It's independent. It's just dependent of its own variable, and the same holds for the third one. You can check it. F1 for z, nothing. F3 for x, no dependence. Also here, the second, differentiated with respect to x, no dependence. The first one for y, nothing. So it should not surprise you that we get the 0 vector, which actually, you must remember, this is not just a single vector. Instead, this means that everywhere, this whole vector field, which is the rotation of another vector field, it's a very abstract concept, gets 0 everywhere in space. So we can say this is the null field, or even the 0 field, to make clear that it just vanishes everywhere. So what does it say? What does it tell us? Well, let's put this in a general form, because it's a general fact. we just found out that the rotation of a certain gradient field, which is the gradient of a potential, gets us the zero or the null field. And it turns out this is a general law, because for a quite simple reason, actually. We have understood that the gradient of a potential is always a so-called conservative field, which means, exactly speaking, it has no vortices. If it had some vortice, put this away, if it had, even if it had a single little vortex anywhere in space, you could just, well, you could locate this vortex, go there, and then make a little journey around and round and get some positive result from calculating the corresponding path integral. The path integral will be actually our next topic then in the upcoming sheet. So since the vector field is conservative, it must hold everywhere that, you know what this means, the closing symbol, a closed path, exactly speaking. This is the special symbol for a path integral along a closed path. So the closed path integral of this vector field f along any closed path must be zero. And this is another way of saying there are no vortices. So the vorticity of this vector field is zero everywhere. And now this is our message or learned. This operator called rotation is exactly the one that calculates the vorticity of the given vector field f, which is in this case the gradient of a potential, and this means it has no vortices at all, and so the rotation will be zero everywhere. I hope you have already reached a certain understanding of what rotation really is mathematically, because it's the case if you have some vortex, the rotation vector itself points in the direction of the vortex axis, so the axis around which the vortex is to be found, and the absolute value of the rotation vector will give you the strength of this vortex. And this happens everywhere in space, so really it's really complicated because the rotation is a vector field itself. You could say it's an abstract transformed version of the given vector field capital F to tell you in a mathematical way how strongly and in which way it is well, its vorticity takes place, if I may say so. Okay, something like this. The opposite, given in words, is called a vortex field, a field which this would be, you could say, a pure vortex field which has no divergence, but its rotation is non-zero, and if its divergence at the same time is zero, you would say it's a pure vortex field. There are also mixed cases. That's important to know, and we will see an example in the next exercise. So we can also call such a field circular. In some way it's circular. It means that the field vectors, like this field vectors are arranged sort of like this in a closed path. Not everywhere or even everywhere, but at least somewhere. So it's not conservative. It has no potential function phi. That's an interesting statement now, because it's the opposite of this case. So if you find a way to prove that a given vector field has no corresponding potential function, because it's simply impossible to find a consistent potential function for this vector field, you can be sure that this field is not conservative. Instead, it will be a pure vortex field, and its rotation will be non-zero. So this is quite the opposite case of this one, right? Okay.